All right, let's go ahead and talk about math. So some quick problems here before we get going with the volume stuff I was planning on talking about today. There's a whole bunch of words that just really say, last time we talked about doing mini U substitutions, where there's all these integrals that you're going to see during the course of your rest of your mathematical career, really, where it's going to be such an easy U substitution that you should really just kind of do it without doing the U substitution. Meaning, if I'm going to integrate sine of 3x, I know it's going to be negative cosine of 3x divided by 3. Or times 1/3 if you prefer. Similarly, e to the negative 1/3 x is going to, the integral is going to equal e to the negative 1/3 x divided by negative 1/3. Which I would definitely simplify as negative 3 e to the negative 1/3 x. Let's see. I should zoom in so you guys can see that better. Same deal here. I know the antiderivative of secant x tangent x is secant x. So the antiderivative of secant of 4x times tangent of 4x is going to be secant of 4x divided by 4, or multiplied by 1/4. It even works if you have something times x plus a little constant. So the antiderivative of cosine of 2x plus 5 is going to be 1/2 sine of 2x plus 5. Let's see. In each of these instances, if we took the derivative of our result, we'd end up multiplying back by that coefficient. If we take the derivative of this, we'd multiply by 2, cancels the 1/2. We took the derivative of this, we'd multiply by 3, cancels the 1/3. Here also works here, right? If you have something where you multiply by x to a large power, you can just treat that as like something to the 18th, whose antiderivative is going to be, let's see if I can fit this in here, 2x plus 5 to the 19th power divided by 19. And what else do I need? Well, a divided by 2. And a plus c, of course. You can really see it now. You really see it up close. And lastly, 1 over 2x plus 5, the antiderivative should be the natural log of the absolute value of 2x plus 5. And then just like in these other two problems, we have to also multiply by 1/2 or divide by 2. So that's what I mean when I say a mini U substitution, something where you're just going to end up, where we could have done the U sub for any of these. We could have let u equal 2x plus 5 here and gotten 1/2 du equal to dx and then done the whole thing, but you don't need to do all that work. Questions about any of those? No, I think you should. I think it's worth asking your teacher, honestly, but really I would generalize and say most people are pretty okay with you doing this amount of U substitution in your head. On the other hand, well, no, I mean, yeah, it really, I was going to say, on the other hand, something like this might be a little different. Let's do this. Let's write one first. So let's say for the integral of e to the x times sine of e to the x dx. There's a point I want to make here. So we can and we should do a U sub here. And the natural choice for u is e to the x. And my du is also going to be e to the x, or it's going to be e to the x times dx. Now, here's what I want to point out, and this is where people sometimes kind of go wrong. If I wasn't being super thoughtful about how I do this, I might start rewriting this integral as, now this is going to be wrong, but I might rewrite the integral of e to the x times sine of e to the x dx. I might be like, oh, well, there's a u, and there's a sine of u. And if I wasn't being super careful, I might just be like, oh, sure, du, that works. That definitely does not work. Because, well, one, dx doesn't just magically become du. They're not the same. So whenever, and this is what I really want to say, whenever you are doing a U substitution, the first thing to take care of is making sure that dx transforms into du. So looking at what dx is, well, du is equal to e to the x times dx. So I'm seeing an e to the x times dx. I might even, although you don't have to, I might rewrite this so that those are next to each other. This is sine of e to the x times e to the x dx. Because then it's super easy for me to say, oh, there's my du. And then the other things left over after I've dealt with du, now I can start replacing with u's. So you can say, oh, e to the x there, that's going to be a u as well. So this really ends up equaling the integral of just sine of u du. And then we can anti-differentiate that and get negative cosine of u plus c, which is then going to equal negative cosine of e to the x plus c. So that's the point I want to stress there, is that if you're integrating something doing u substitution, we really want to make sure we transform dx into du before trying to replace any of the other things with u. And this other problem over here is pretty much the same. I just wrote a second example because I thought it was maybe worthwhile. This other one is the integral of e to the x cosecant of e to the x times cotangent of e to the x. And we would do the same thing, meaning we would still let u equal e to the x. We would still see that du is equal to e to the x times dx. And once again, we would point out that right there, those are the things that make up my du. So when I start rewriting this, I really do write first just the integral of du. Okay, those things have been erased from my mind. What's left? Cosecant of e to the x cotangent of u, or cosecant of u cotangent of u. And then we have to think of the function whose derivative is cosecant of u times cotangent of u. And we know that the derivative of cosecant of x is negative cosecant of x times cotangent of x. So the antiderivative of this should be negative cosecant of u plus c. And then going back to the function we started with, that's negative cosecant of e to the x. Questions, comments from the Zoom folks? Right, well, let's move on. So again, we'll keep coming back to u substitution. It's going to come up all the time. Just be aware of the process. Let's see, do that one first. That one. Sure, let's do this one. So yeah, we'll start with this and we'll do it that way. Let's do this. Here's an example that someone, Grant, has already drawn out. It's lovely. He's great at drawing. I'm okay at drawing. So let's look at this. We have this shape, which is kind of like a tent kind of looking thing. And we want to find the volume of the quote unquote tent, shaped solid, formed by the intersection of two quarter cylinders of radii 3. So this is the quarter of a cylinder of radius 3. This is the quarter of a cylinder of radius 3. And we're seeing where they intersect in this kind of shape here. So when I look at this, I see there's a quarter of a circle right there. There's a quarter of a circle right there. These other surfaces over here are kind of weird. So how are we envisioning finding the volume of this thing? Well, as is typical, whenever you're trying to do something where you're finding volume or area or whatever, we're essentially adding up slices. So back when we were finding area, which I know it was just like the other day, way back when we were finding area, we were adding up little slices that were each rectangles, or I call them strips often. That idea is going to be pervasive. We're going to do that for finding volume, for finding, what else? There's other examples for finding surface area, for finding other things. It's always going to come back to, well, take a slice and then see how you can calculate the whatever of that slice, the volume, the surface area, the thing, and then add up, integrate to get the total of all the slices. So here, our slices are going to be cross sections that look like squares. Right, this bottom part here, definitely a square. And as you go up and up and up, you're always going to get a square shape if you take a cross section that is parallel to the XY plane, parallel to the floor, which I'm thinking of as the XY plane, although that's not how we've labeled it here. All right, so here's what we are thinking. Cross section to the height of X from the bottom. So we're going up to a height of X are squares with a little thickness, dx. Okay. And then the squares have a side length of y. How are we going to figure that out? Well, let's see here. So here's my shape. Here's my cross section with a quarter of a circle. And I'm thinking of that square having this side length of y. And being at a height of x. Okay, well, I also know that this quarter here, this quarter of a circle is of a circle of radius 3. So I can say, well, this length here, that length is 3. And then I can find an equation for y in terms of x. I can say that x squared plus y squared has got to equal 3 squared. Some Pythagorean theorem. And if I solve for y, actually, I don't even want to solve for y. I could solve for y. But since I know I'm going to find the area of the shape, which is y times y, I'm going to not do all the work I don't need to do and just say that y squared is equal to 9 minus x squared. And that is the area of my slice at a height of x. So let's think about this for a second. At the very bottom, right way down here, here's a slice with a little bit of thickness. It's at a height of essentially 0, and its area is 9 minus 0, which is 9. That makes sense, right? The area at the bottom should be 3 by 3, which is 9. Whereas if you go up all the way to the top, where x is 3, you're going to get a square that has 0 area to it. So it's good to think about what happens at the very end. At the bottom, yeah, it makes sense. At the top makes sense. And somewhere in the middle, right, like we went to, like, I don't know, if we said this was like, too high, then this square would have an area of 9 minus 4, which would be 5. So we're thinking of each of the sides being a length of the square root of 5. So yeah, as the squares move up, the areas get smaller. So this is the area of my cross section. So each slice has a volume, so I said volume, of area times thickness. And then what are we going to do? We're going to add up all the volumes. So we're going to get the total volume by adding up all the volumes. We're adding up all the slices. And that's how we're going to integrate from a bottom of x equals 0 to a top of x equals 3. Of 9 minus x squared dx. So what I want to point out here is that the setup is the harder part. This integral is not hard to do. We can definitely do the integral from 0 to 3 of 9 minus x squared and get 9x minus x cubed over 3 from 0 to 3 and plug in 3 and get 27 minus 27 thirds and plug in 0 and get 0 minus 0. And that's going to be 27 minus 9, which is 18. Actually calculating that is not that challenging, but setting it up is the hard part, I think. So here's what I'll say about this particular problem. These are kind of your least typical volume problems. So they're not really anyone's favorite. Some people will skip this entirely. I'm going to show you like one more, maybe two more, and then we'll move on to the more typical types for the volumes of revolution. So let's look at another example here that I wrote down somewhere. Maybe somewhere. Yeah, kind of. Hiding from me. You know, I like to hide stuff in the soul. So let's see here. I know I wrote you down somewhere over here. I just hidden you behind all these other pieces of paper. Maybe I wrote it down, I promise. Fine, I'll just write it again. The problem with these problems is the phrasing of them is always like, let me see that the right way. So here's what I've got. Oh yeah, there we go. I see it. So we want to find the volume of the following shape. And I found that the easiest way to describe this is by talking about the base and then what the cross sections look like. So the base is the region bound by or bounded by the x-axis and the parabola y equal to 4 minus x squared. So that's the base. That's what we should be thinking of, sitting in the xy plane, kind of on the floor. And the stuff's gonna like pop out of it. So cross sections perpendicular to the, what have I picked in this time? To the y-axis are right triangles whose hypotenuse runs across the base of the solid. And I will admit, just reading this without having seen something like it before makes it difficult to conjure what the image should look like. But let's break it down. So I have got my base, which I'm going to draw it in two different ways. So here's the first. I'm going to draw it. So y equals 4 minus x squared, downward opening parabola, y-intercept of 4, x-intercept of 2, and negative 2. I don't really want all of that, but I drew more than I needed. So here is my region and the region I'm looking at. And then here's what we're saying. We're saying that cross sections perpendicular to the y-axis, so running perpendicular to the y-axis, parallel to the x-axis, are right triangles whose hypotenuse runs across the base of the solid. So right triangle, the hypotenuse of the right triangle maybe is like right there, a little bit of thickness. And then that's the hypotenuse. So the other two legs are going to be kind of making a tent shape popping up like that. This is where my drawing skills are going to start to fail. But essentially we've got, see? And then, fine. That's okay, I guess. Hopefully you can kind of see what I mean there. There's one of my triangles. My right triangle. And then as they move up towards the vertex, the triangles will get smaller because the base is less wide. So like up here, you've got a much smaller triangle. And then down here, you've got a way bigger triangle. It's nicer to try and draw it from a different perspective. So let's do this instead. Let's take the shape, and often we're doing it this way. We like to kind of draw, I like to draw the x-axis here and the y-axis here. And so I'm going to just kind of wing it. Which is always a good plan. Here's my parabola, kind of. That's pretty good. Not all right. So there's my parabola, my base, and then here are my cross sections perpendicular to the y-axis. Forming a little right triangle. Right? Oh, it's way better, right? You guys are like, oh, we can actually see a thing. And zoom in even. All right, and here's another one over here that's a little bit smaller. And so one sec. So then we go full on big here. The idea is that if you kind of like connect all these little shapes, you've got this kind of shape that looks like that. Again, my drawing skill is not amazing, but kind of get the idea, I hope. No. Not if you not well, it depends on what you're calling the base and the height. If the base and the height will reach legs of the right triangle, sure. I said that the base of the right triangle, let's see, cross sections perpendicular to the y-axis are right triangles whose hypotenuse runs the base of the solid. So the hypotenuse is this side, and these are the two sides that are the same length. Well, if you want to call them that, sure. But the way it's oriented, I'm calling this the base and this the height. Right? So my right triangle looks like this. That doesn't look very right. There's my base. I'm sorry. And there's my height. See what I mean? I mean, you could do it that way, sure. I'm drawing it as described. So I'm drawing it so that the hypotenuse, right? Cross sections perpendicular to the y-axis are right triangles whose hypotenuse runs across the base of the solid. So the hypotenuse of the right triangle is what's running the length of the base there.
Really quickly, could you have solved the problem the same exact way by assuming those two to be based on the height and taking the formula of those two? If they're the same.
I'm not sure what you're saying exactly.
Okay, I can show you.
I'm trying to find the this and whether it makes sense.
Sure, I was thinking, could we find the area of that using the hypotenuse of one as the hypotenuse and assuming that because these two are the same, they will be 45.
Yeah, totally. Yeah,
That
definitely.
work?
Yeah. So we need to find the area of these triangles so that we can multiply them by a little bit of thickness. So the volume of one of these slices is going to be the area of your triangle as a function of y times the thickness. So to find the area of this triangle, we really need to find out what the base is. All right. So, so here's what I should point out because it's kind of nice. Really, the area of this triangle is just half the base squared. Because you can think of it as being so cut this in half and then flip this over. So you've got a square. Right? Right, you can cut that triangle off and then you can go boom, 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 there. And then there's the other half there. Kind of like that. Or you could like do more math and be like, I can find the base and then take half the base and multiply by, you can do trig, I guess one, two, I don't know. Okay, so to find this here, we have to find this length. So we have to essentially do this side of the function minus that side of the function. So that function is y equal to 4 minus x squared. And if we want to do the right side minus the left side, we have to write x as a function of y. So we have x squared equal to 4 minus y, x equal to plus or minus the square root of 4 minus y. The right side of the function is x equal to positive square root of 4 minus y. The left side of the function is x equal to negative square root of 4 minus y. And the right side minus the left side is the square root of 4 minus y minus the negative square root of 4 minus y, which is just going to be 2 times the square root of 4 minus y. So that is the length of your base of any triangular cross section. And then we want to find the area of this right triangle. So we take your base and you can take half of it and square. But I can say more about it if you really want. So just to make sure everyone's on the same page here, if this is your right triangle, right, if this is your base, well, we know for a right triangle, if you write it like this, the sides are like a 1 root 2 kind of deal, or really an x root 2 kind of deal, or really x over root 2, x over root 2, x kind of deal. So if the hypotenuse is the side we have, then these other two sides are the base divided by root 2 and the base divided by root 2. And then if you find the area of this, it's 1/2 base times height. So flip it around that way. Wow, my right angle is really not good. It's a terrible right angle. But if you do 1/2 base times height, or 1/2 base over root 2 times base over root 2 is going to be 1/2 times 1/2 times the base squared. I know it's kind of silly to do it that way, but that's what we've got. So this really is going to be one-fourth times our base, which is this, times dy, which ends up just being 4 minus y dy. All that for something that's not too terrible to integrate. So that's the volume of a slice. Right, I know, it's like, it's funky. Let me back, so let me say one more thing before I come back and clarify. So that's the area of, I should say, that's the volume of like this little triangle right here. And then we're just adding them all up from y equals 0 to y equals 4. The rest of this, which is not terrible at all, you get 4y minus y squared over 2 from 0 to 4. That ends up being 4 times 4 minus 4 squared over 2 minus 0 minus 0. It's going to be 8. So let me clarify two things. Thing one, the length of this base is just this right function minus this left function, which is the square root of 4 minus y minus the square root of 4 minus y. That seems not too terrible here. I feel like I was a little hand wavy with the area of this right triangle. So let me just reiterate how I got there without making it terrible. Here's my right triangle drawn, maybe not terribly. And here's what we have. We have that this side here, this is 2 times the square root of 4 minus y. That is the length, which we can just call L if we want. And let's do the easy thing, which I was not doing before because I don't know why I wasn't doing it before, because I was trying to make my life harder than it needed to be. This length here is half of that. This height here is the same as that because it's a new right triangle that's isosceles. So the area of this triangle is 1/2 the base times the height, which is just that, which is just which is just 4 minus 1. Hopefully that's a little bit of an easier way to see it. What I would say typically, and you probably won't see many of these problems at all because no one likes them. Typically what you want to do is you want to just talk about the base of your region in terms of like saying, oh, let's just call that L and then figure out a formula for the area based on L. And then after you've done that, plug in what the length actually is. Okay. We got enough time. So we'll come back and do another one of these a little bit later to remind ourselves of how much they suck. But let's move on to the more typical discussion of volume, which is volumes of revolution. Sometimes it's nice to kind of talk about shapes we already know. For example, let's find the volume of a sphere of radius Yeah, let's make it really sucky. Let's make it a radius A. It's nicer when people use numbers, but sometimes your book doesn't use numbers and the cheat doesn't use numbers. So we'll do one where the radius is just some generic constant. So how are we going to do this? Well, we're going to do this by revolving a semicircle, or the top half, a semicircle of radius A about the x-axis. Let's take a look. So, you're welcome. I'll see you later. Here's my semicircle of radius A. So this point here is A comma 0, negative A 0, 0A. And here's the idea, just like every other time. We're going to take a cross section, a slice, and we're going to rotate that slice. So typically, if you're talking about, back down to the triangle area explanation again. I can put that back up later, but I really want to continue on with this one. So I will get that back up a little bit later. So the idea here is that we're going to take a slice perpendicular to the axis of rotation. And I'll just make a blanket statement now, which I'll say again later. When you're using the disc or washer method, you always want your slice to be perpendicular to the axis of rotation. Whereas when we start using the shell method, you want your strip or your slice to be parallel to the axis of rotation. And what I always remember in my head, my mnemonic device for that is shell is parallel. And the other one's perpendicular. So here we're going to rotate this half circle around the x-axis. So here's what happens when we do this. We're going to get a sphere, right? If you rotate this half circle around the x-axis, full 360 degrees, we're going to get a sphere. And if I can draw it all right here. Look like this. But importantly, if you think about what happens to this strip when you revolve it around, well, that strip, living like right about there, is going to do this. It's going to make a little disc. And that disc, well, if I just draw it over here for a second, that disc has a little bit of thickness, right? The thickness is a small change in x. And the area, the volume of this disc is the area of that circle multiplied by the thickness. So if I call this for a second the radius of that disc, then the volume of this slice is pi times that radius squared times the thickness. But we can figure out what that radius is. Right, this radius here is not the same as the radius of the circle. Right, I'm talking about this radius here. But I can figure out what that is often by using the Pythagorean theorem. So check it out. If I do this, right, if I do this, this, and this, if I say that we're at a distance of x from the origin, then we know that that radius there, well, we know that x squared plus r squared is equal to a squared. So that my radius, r squared, is a squared minus x squared, or r is the square root of a squared minus x squared. Now, I did more work than I needed to there, because what you would really do is you would just say, hey, the top half of this circle, we know the function for that. That is y equal to the square root of a squared minus x squared. And then so you would just say, oh, the height of that function is how high the height of that strip is. That's what my radius is. It's just how far the function is away from the x of rotation. So this is going to equal pi times our radius squared times our thickness, which is just pi times a squared minus x squared. All right, so that's the volume of one little slice. And now we want to add up all the slices. How far left do my slices go? All the way over to negative a. And how far right do my slices go? All the way over to. So the total volume here is going to be the integral from negative a to a of pi times a squared minus x squared dx. All right, let's go ahead and do the integral. So I'll remind you, even though it kind of looks like it's not, a squared is a constant. So when we integrate this, we get pi times, let's see, the antiderivative of a squared is just a squared times x. The antiderivative of x squared is x cubed over 3 from negative a to a. And if we plug in a, we get a squared times a, which is a cubed, minus a cubed over 3. Minus, if we plug in negative a, we get a squared times negative a, which is negative a cubed. Minus, if we plug in negative a, we get negative a cubed over 3. This ends up being pi times, let's see, a cubed minus 1/3 a cubed is 2/3 a cubed. And negative a cubed plus a cubed over 3 is a negative 2/3 a cubed. And so we end up getting pi times 2/3 plus 2/3 is 4/3 a cubed. Or if you prefer, 4/3 pi a cubed, which is what we know the volume of the sphere is. 4/3 pi times the radius cubed. So the nice thing to see here is that it works. Right, the formula that we are knowing is true for the volume of a sphere is actually borne out by this process of using what's called the disk method. Let me go back real quick just because someone asked for it. Here's that triangle shape that I had drawn before, just so you can see it again in case you want to see it real quick here.
So this one's called a disk method. You think something about shell with parallel?
Correctly, sure. We'll get to the shell method maybe either Wednesday or Friday. But the shell method gives you a totally different shape. So,
This method, we're just rotating it around the y-axis, right?
well, no, wait, which axis do we rotate around?
X-axis.
Right, the axis.
Yeah.
So here's the thing. You can use the shell or disk method for rotation around either axis. The thing that has to remain true is that if you're using the disk/washer method, that your strip has to be perpendicular to the axis of rotation.
Okay.
So let's do another example. Let's say we want to find, we should have enough time to finish to do both of these. You're welcome, yeah. So let's find the volume of the solid formed when the region R bounded by y equal to 1/4, y equal to 1/9 x and y equal to the square root of, is that what I really want? 1/4. Sorry, let me think for 1 second here. 4, sorry, that seems weird. That'll be fine, I guess, although funky, sure. 1/9 is too big, although. Make that y equal to 1/5 x. And y equal to the square root of x. Sure. Is revolved. Let's first go around the x-axis. So I'll point out, usually isn't required that we draw the region, but it's often helpful. So let's think about what this looks like. I know what y equals 1/5 x looks like. It's a straight line that goes to the origin. Square root of x is the usual shape, and these are going to intersect somewhere. Now, instead of setting them equal to each other and trying to solve them, that's probably not hard. We could also just guess likely numbers. So I'm going to guess some square numbers that is going to make this an integer. But I want that square number to also make this an integer. What's the only square number? What's the smallest square number that if you divide it by 5 is still a whole number? Let's see, 4, no. 9, no. 16, no. 25, yeah. So if we let x equal 25, does that work? It does. Square root of 25 is 5, 1/5 of 25 is 5. So often if you're paying attention, you can guess the point of intersection pretty easily. We could also solve this. It's not too terrible. If you set square root of x equal to 1/5 x, I might just multiply both sides by 5 first. 5 root x equal to x and then square both sides. 25x equal to x squared, and then bring everything to one side and factor. And then you get the solution x equals 0, x equals 25. So typically solving it is maybe not terrible, but it's often nice if you can just guess. So here's what the region looks like. You've got your y equals 1/5 x, and you've got your square root of x. So if we're going around the x-axis, we are going this way. And so we're going to draw a strip that's vertical or horizontal. Well, so far I've said the strip has to be which orientation? Parallel or perpendicular? Perpendicular. So if we're going around the x-axis, which is a horizontal axis, I need my strip to be vertical. And now when I rotate that strip around, there's going to be a part missing in the middle, right? It's not going to be like before where the strip was right next to the axis of rotation, like in this previous example, right? When I took this strip here and rotated it around, I wasn't missing anything in the middle because it was right next to the axis of rotation. But here, since there's all this space here, I'm going to be missing the middle part of this washer. So when I rotate that part around, and I often just like to draw the part here, right? If I draw that, and think about rotating, sorry. I don't like drawing the whole 3D shape. If I can. Well, I'll show you. So I'm going to draw that, flip it over. Again, also not necessary to draw this. What I'm drawing here is kind of the idea of this area being rotated around the x-axis to get this volume, which kind of looks like a bowl, but the insides are kind of conical shaped. So it's like I took like a solid like dome kind of thing and cut out a cone from it. But look what happened to my strip. My strip here, if I rotate that over, is going to look like this. I'm going to be missing the inner part. Which doesn't look great there, I'll be honest. But the idea is that basically we're taking this little section here and we're saying, okay, well, I'm rotating that part around and I'm totally missing this middle circle. Well, great. I can find the volume of one circle minus another circle with some thickness. The volume of this slice is going to be pi times the larger radius squared minus pi times the smaller radius squared times the thickness. The larger radius is the function that's further from the axis of rotation. So here, my large radius is going to be the square root function. The smaller radius is the function that's closer to the axis of rotation. And my smaller radius here is going to be 1/5 x. So actually using the functions we've got, the volume of my slice is going to equal pi times the square root of x squared minus pi times 1/5 x squared, all times dx. And then if you want to time, and I'm just going to set it up since we're almost out of time here. If we want to find the total volume, we're just going to do the integral of all that from, well, my slices go as far left as x equals 0 and as far right as x equals 25. So we do the integral from 0 to 25 of, now what people almost always do for this is they factor out the pi, because you're going to have a pi multiplied with those things. So we have pi times the integral from 0 to 25 of the larger radius squared minus the smaller radius squared. What I'll try to say quickly in the last minute here is we get a totally different result if we go around the y-axis. Let me just show you how to set that up real quick and then we will be done. So if instead I take my region and I go around the y-axis. Oops, sorry, you can't really see that very well. Apologies. Well, I have to use a strip that's perpendicular to my axis of rotation if I'm being forced to use the disc or washer method. So here my strip is going to be horizontal. And so when I rotate that thing around, well, when I rotate it around, here's what it's going to look like. There's my washer. So I will point out, the disc and the washer method are both taking the same idea. You're taking some strip perpendicular to your axis of rotation and rotating it around to get either a disc shape if there aren't any missing parts in the middle, or a washer shape if your strip isn't exactly up against your axis of rotation. But it's the same idea either way. And so then I know that the volume of my slice is going to be, well, it's going to be pi times my large radius squared minus pi times my small radius squared times my thickness, which in this case is going to be a little dy, because the thickness is a small change in y, not a small change in x. Right, literally, like the thickness being vertical just means you're going up a little bit, which is a change in y. Whereas over here, the thickness being horizontal, that you go a little bit to the right, it's a small change in x. So when you've got vertical strips, your thickness is dx. When you've got horizontal strips, your thickness is dy. And that tells you which variable you have to integrate with respect to. So I know I'm over time, but let's just wrap this up. If you need to go, you're welcome to go, but I'm about to wrap it up. So you can stay if you want as well. So those are my functions, y equals root x, y equals 1/5 x. But now the function that's further away from the axis of rotation is, well, this one here, except it's now going to be x equals 5y. That's my large radius. And then my smaller radius is the closer function, which is going to be, well, x equals y squared. Right, y equals root x. So then the volume of my slice is going to be pi times my large radius squared, so 5y squared minus my small radius squared, which is going to be y squared squared. And then my total volume would be, well, I'm going to add up all the slices. It's going to be pi times the integral from y equals 0 to y equals 5. And because this point here is the point 25, 5. So the x's would go from 0 to 25, but the y's go from 0 to 5. And then 5y squared minus y squared. And just for context, if you're interested, not that it's really important, but if you want to draw like the kind of what the rotated shape looked like, here's my tips for drawing the rotated shape. Draw the outer boundary of the side you've got. Right, this is the part that's further away from the axis.
You just flip it, right?
Right, and you flip it over, exactly, you flip it. Then you try and draw like the inner part dashed, because you're gonna be covering it up. And then you kind of rotate it around. And you can kind of see that there. To me, what I always think of when I think of this shape is, have you ever been to the mall and they have those things you put like a quarter in and like goes around and around, or a nickel if you, right? You put a nickel in because obviously you don't want to put a quarter in there, and it goes like around and around and around and around, and goes down the whole bottom. That's what this kind of reminds me of.